Hello everybody, I'm Mert Vadar from TR Transmisyon company. Today we are together for the first virtual member focus session of BGA. I thank for the organization that give me this chance. So today we will talk about the orbicular gear mechanism and its kinematics, what is already patented by me. So let's start with our R&D company, TR Transmisyon. We have a partnership with Hexagon Group. We are the engineering partner of Romex technology software in Turkey. We are giving the technical support of the software, and also we use the Romex software in our development projects. Also, we can use all the Hexagon software family on our complicated advanced analysis. What we can do for our customers, we are mainly specialized on high-speed and aerospace sector gearbox developments. We can make complicated transmission system level analysis. Of course, we can do microgeometry analysis, also the system structural, dynamic and thermal analysis. We can also make CFD and lubrication and the efficiency analysis. If we turn back to our topic today, we want to talk about a new art of orbicular gear mechanism kinematics. As you all know very well, the traditional planetary gear mechanisms have one external sun gear encircled by planet gears and also one additional internal gear. This kind of mechanisms have some limitations in size, weight and load distribution. So sometimes in some applications they can fall short in requiring some compactness, weight reduction or various applications. So what we concentrated about is a new orbicular gear mechanism just to overcome such kind of disadvantages and the constraints. Actually, what we call as OGMs, they have two face gears. One represents a sun gear and the other one represents a ring gear. And we also have the same planetary external gear systems. But when we make such kind of mechanism, this can bring us several groundbreaking advantages. Actually, we can maximize our planet numbers and relative to the gear ratios. Also relatively smaller than the traditional epicyclic gear mechanism. And also offers more unchanged load distribution. It can achieve significant amount of weight reduction in some applications. We will also inspect one kind of application in this presentation. It is easily mounted for low backlash operation. We can just minimize and approximately make it zero in some low speed applications, these centrifugal effects. And because of we just mount our planet gears on a perpendicular axis of carrier rotation, we can easily manage these centrifugal effects loads more easily than the traditional epicyclic one. Of course, we will be more concentrated on the advantages. This study is just a beginning for us, because what I want with this patent release, just want to take some attention on this kind of mechanism and the kinematics, just to inspect more gear engineers, to inspect the advantages and disadvantages of the system. So let's start with the prior art of epicyclic mechanisms and the kinematic tables. As you know that thanks to HMEA, they already standardized this kind of planetary gearbox systems, and we already have some different variant tables for each kind of planetary configuration. As you know from the standard, they just try to explain gear arrangement for different kind of planetaries, like it is the basic one. As you know, we have one ring gear, one sun gear, and planets, and one planet carrier. But we can also make some variations on, as you see on the other tables, like the gear arrangement B, C, D, E, and F. We just can increase the number of the ring gears, number of the sun gears, also number of the planets with the increasing the pin numbers, what I mean. But they already make the direction of rotations, speed ratios, and kinematic explanations of the prior art. Based on the existing table, as you see, we have different variants to just make different arrangements for planetary gear mechanisms. It's also very widely used, different kind of arrangements for different kind of industries, based on what you need, actually. But as you already know, we just use two external gears, like represent our sun gear and the planet gear, and one internal gear, it represents our ring gear. But basically it works with the same logic. So the torque amount on your system will be the most dominant factor about your diameter, but these gears with the same tooth number, as you see in the table, these will be increased like the same methodology from internal, for the external gear from inside to outside, from internal gear from outside to inside. It has the same logic, but as you know, we have some, when we are creating planetary designs, we also need to make some center distance correlations between them, because as you know, we are just making the system in one single axis. So we need to make some arrangements between the planet sun gear mesh and also planet ring gear mesh. So it needs to be an important parameter for us. And also one of the biggest advantage of this type of gears, we don't have any limitage about the phase width. I mean, it is independent from your module. Of course, when you use some helical gears, you still have some boundaries not to increase your phase width length too much because of the tooth bending. But for the spur gears, especially, it is not dependent to your module, so it has an advantage based on this point of view. About the new art of orbicular mechanisms and also its kinematics, we just try to find the gear arrangement alternatives when we try to simulate them, as you see, with the new mechanism. For the orbicular one, our sun gear will be represented by a phase gear, and our ring gear also will be represented by another phase gear. So we still have the external planet gears, But as you see in the tables, what is the main difference between them? Our planet gears are not rotating in the same parallel axis to our carrier. Now they are rotating on the perpendicular axis of the carrier. So what we try to do is we just try to calculate all the speed gear ratios, direction of rotations like already represented in HMEA. But we follow the same logic for different gear arrangements of the orbicular ones, like we follow on the prior art of epicyclic ones. So after we formulate all of the gear arrangement tables, like based on the prior art, we just try to find what advantages these kind of mechanism brings us and what disadvantages it will bring. When you inspect a phase gear, when it increase the modules, as you see, we also have the same diametral issue. When we increase our module with the same tooth number, it also increase the module. But it has a disadvantage based on the external and the internal gears, I mean about the phase gears. We have a limited phase width based on our pressure angle limitation. But also we bring some advantages that we can make some compact gearbox arrangements, and also when we want to locate our planetaries. Our planetary location is based on this direction, so this will not increase our gearbox size radially. It has more compact. Actually, when you just imagine how it works, the best definition, I think it can be like one is like a radial flux engine, radial flux motor, and the other one like working like an axial flux motor. So this logic behind it, we just concentrate about more details, which arrangements can be useful for the current developed systems, and I just want to share with you one application example, and we will start to inspect it. So let's start with an application example. As you see here, you can see a conceptual model of one of existing helicopter planetary final stage. As you see, they already use 6 planets, and our reduction ratio is approximately 3, and our floating ring outer dimension is approximately 520 millimeters. Of course, for the equal load distribution logic, our tooth number of ring and plus sun tooth number can be divided by our planet numbers, can be divided by 6, and it's an integer. Our module is approximately 3 millimeters. Gears are spur, there is no Hellis angle. Approximately 1250 horsepower. Power transmission can be allowed. Lower reduction ratio based on some control rods and this wash blade assembly inside of the sun gear. So we have some limits around the planetary construction for the helicopter. But you can see the details about the carrier RPM. I mean, it is the A-type traditional one. Our ring gear is fixed, our sun gear is our input, and planet carrier is our output. So we have the same A configuration planetary gear system arrangement. As an aerospace engineer, most of us try to find how to improve our existing designs. One of our goals, if we have an existing design, how we can improve these kind of arrangements to make more benefits, especially about the weight. So let's put some targets to improve our existing design. We just try to find some questions. Can we increase the planet numbers and reduce the weight of the bearings to have some weight reduction? Actually, one of the most important question is this. If the answer is yes, okay, increasing the planet number will also decrease the planet size. So it means that when you decrease the planet size, it means that you increase the speed. So can we decrease the centrifugal effect of these planets when we try to make this arrangement? We also try to answer these questions. So if we increase the planet numbers, we also need to make more precise manufacturing on our carrier, of course. So we also try to discuss is our improvement worth it or not worth it. And the most and the only the most popular question for the aerospace engineers: can we make an improvement of the weight reduction? This is the most important question. Okay, so let's start with the old methodology. When we try to make some improvements on our current planetary system, let's use our current methodology. Just make the A variant to B variant. If we can increase the number of planets, so distribute more load, more torque, and we can decrease our planet bearing size. And can we have a weight reduction with this methodology? Just start to inspect it. So we will use the same methodology that we have a fixed ring. We have the sun gear input and we have the carrier output. So like the same methodology on the A gear arrangement, but we just divide our planets from one planet to two planets. And okay, when we make this, we can decrease our module just 2.5, and we can make the arrangement with 12 planets instead of 6. So this means that we have much more, half of the load torque comes to the planets. Our reduction ratio is again approximately 3, and the ring gear size approximately dropped to 450 millimeters, so it's not bad. And we still have the approximate 1250 horsepower power transmission, nothing changed. And we also have the same low reduction ratio based on the control rods, wash plate assembly inside the main rotor. So we still have the gap to allow it. But the main problem when we use the old methodology, as you see, that same center distance cannot be provided with the same module of the gears. So we still need to modify our gears to catch it. I mean, as you see that we have the planet carrier, one axis is here, one axis is here. We still need to cross these axes on the same line just to make a healthy one pin distribution like in the B variant. But we still need to play, and we still need to make some design arrangements to catch it. And also, as I mentioned in the previous slide, when we decrease our planet sizes, as you see here, we just increase our planet speeds nearly 2 times more. So this brings us a disadvantage of the centrifugal effects. And we can make a center distance arrangement with some module modification. we still have a problem that our planets are more fast, and we still have these additional centrifugal effects. So about the prior art, when we try to make one planet A arrangement to B, yes, we can see that some gear pairs can be more smaller, but we still have some disadvantages also about the centrifugal effects and the center distance problem that we need to make the modules more special for the application. So let's inspect the same system with the new art of orbicular gear drive. So we will use the same arrangement like the B, but it will not be the epicyclic, it will be the orbicular, and we will use the same fixed ring gear. Input is sun gear and the output is carrier, and we also have the same direction of rotation. We have the speed ratio, so we just arrange the gears with these numbers. So we can have definitely 12 planets for the load distribution. Our reduction ratio is approximately 3, so it is the same. Our ring gear size approximately 450 millimeters, so we reduce the size, it is good. Module decreases to 2.5 millimeter from 3, so our gears are a little small. We can still transmit 1250 horsepower of power. So the lower reduction ratio based on the control rods, they are the same. So we still have our wash plates and control rods inside the main rotor shaft. The most beneficial side is, as you see, we don't have any boundaries about the same center distance, because as you see that we can arrange our center distance between two planets, just arrange the phase gear axial distance between each other. I mean, we have a very high flexibility on there, so we can just make very compact, and we can just put these same number of modules at the same distance, and it will make our life much more easy. And also we have the same problem like we did in the previous art. As you see, we just decrease the size of our planet gears. So this means that we have again the same problem, that we increase our planet speeds. So these planet speeds will affect us about the centrifugal loads, but the main advantage of this system, our centrifugal load direction and our carrier turning direction are totally different. So what we can do, we can just make a slightly helix angle for these two different gear pairs, and we can cancel the centrifugal effects nearly zero. It will be one of the best advantage it brings us. So after making the inspection, just turn back to our targets. We ask some questions at the beginning of the improvement to ourselves. With the orbicular gear mechanism, can we increase the planet numbers and reduce the weight of the bearing to have weight reduction? Yes, we did. So increasing the planet number will decrease their size and increase their speeds. Can we decrease the centrifugal effects? Yes, we did it, and we made it almost zero. We still can handle all the radial load with just single roller bearings. Very small and very lightweight. So if we increase the planet numbers, because we have 12 planets, so we still need to make more precise manufacturing on our carrier. Yes, actually we still have the same sensitivity. I mean, we make the manufacturing more harder, but is it worth it or not worth it? Actually, with the new art of design, it seems to me very promising that we can make little much effort on the manufacturing side. And the most important question, can we reduce the weight of the system. And when we compare with the existing and the new one, we approximately 30% weight reduction on the final stage of assembly. So as I told, this seems to me very promising. What we will declare on this year's fall technical meeting, we will give all of the details what we did about this application, and you can read this all parameters from this article. I just try to summarize you very shortly what we can did as an application example. So based on what we did, thanks to Romex, that we can model system levelly this orbicular planetary system also. As you see on the right side, we have the traditional planetary arrangement, and on the left side we have a orbicular mechanism, and it seems to me very promising about the size. Also for the bearings, also for the ring gear. As you see, we have much more smaller diameter ring gear, and of course we have much more planets with the same ratio. So we just inspect one special industry application example from the aerospace industry, but as you know, in the gear industry, gear engineers have much more different concerns and trying to improve their existing systems. One of the other main concern is low backlash planetary applications. As you know, for the traditional epicyclic mechanisms, you have to achieve a very high precision tooth thickness tolerances when we inspect the gears for some planet, I mean external to external gear, and also planet to ring from external to internal gear. We just try to achieve a very high precision tooth thickness tolerances, just lowering the system backlash. But in contrast, the orbicular gear mechanisms can be very easily mounted with zero backlash configuration. As you know, we have a face gear, and this 2D sketch, when we just cut it from one section, the face gear is just like a rack of the gear, and you can just easily move this face gear on the Z direction, make a double flank connection to your planet, and also in the orbicular mechanisms you can easily contribute zero backlash configuration planetary systems. One of the other advantage for using the orbicular systems, if you need a lower ratio planetary gearbox, this can be very easily managed with the orbicular drives. So I can just hear you who needs a lower ratio planetary gearbox, but in some applications in the gear industry, like as you know, we can make some back-to-back mechanical closed loop test rigs. Just to summarize what is the logic of this test rig, as you know, we have one test gearbox and one slave gearbox, but when you try to make this test system with a mechanical closed loop, you need a planetary units. One will be static, one will be loading planetary unit, and you just reduce you just cancel your reductions between them, and there is a mechanical closed loop power transmission like this. And when you use a loading planetary unit, as you know that with the traditional planetary system, the minimum ratio you can do is 1.7, and this means that when you try to load your test gearbox, this means that you try to load your sum gear. You need to load your ring gear with a much more higher value because of the planetary ratio. But with the orbicular gear mechanism, when you use them, you can incredibly reduce your ratio to 1.001, something like that, and you can just decrease your hydraulic loading unit capacity, and it can be also another advantage of this new art system. As a conclusion of my presentation, the most important thing, I think, is the standardizing the phase gear engineering will be incredibly important to all of the gear industries to make some studies on this kind of new orbicular mechanisms. And as you know that phase gear engineering is still a very hard topic, and it is not very common like the other types of the internal and external gears. And mostly the aerospace sectors are more concentrated on this type of topics. And if the gear committees starts to create some platforms to in the field to collaborate, people share insights and contribute to the advancements in orbicular gear technology, it will be incredibly helpful for also different sector of the gear engineers will make some studies on their existing designs and also need for their new developments. About the future studies, as you understand from the presentation, we mainly concentrate on the advantages of this new mechanism. But as you know, when you start to work on very technical detail on this kind of new mechanisms, it is essential to acknowledge that these mechanisms can also present several disadvantages in also various industry applications. Therefore, this patent aims to further explore these different application scenarios, delving into the mechanism characteristics in greater detail. The analysis of the phase gear microgeometry, contact load distribution still remains highly advanced subject for the gear community. Standardizing such gears and establishing phase gear engineering communities with the support of gear societies, of course, would greatly benefit gear engineers to engage with these novel new orbicular gear mechanisms and just to compare their advantages and disadvantages. And also, despite the numerous advantages of this kind of new mechanisms, as you know that we also need to very deeply technically analysis all of the new concept gearboxes, considering its dynamic, structural, thermal characteristics, also includes the aspects such as lubrication and efficiency. Thank you for listening.